And we found that this circular current carrying loop, okay, behaves like a magnet. Basically, this is what we call as an electromagnet. One side where the field points into the loop, that behaves as the south pole of the magnet. The other side where the field points out of the loop behaves as the north pole. So we call this as a magnetic dipole. Right. The field produced by it. Let us discuss this formula in detail now. When R is much greater, okay, when X is much greater than R. Yeah. So this was the magnetic field on the axis of a circular current loop of radius R. Fine. Now we noticed some similarity between this formula for axial field to the formula for axial field of an electric dipole. Okay. Axial field of an electric dipole is 2kp by x cube. Okay. Let us draw an analogy between these two. This is for a magnetic dipole, particularly a circular current carrying coil on its axis. This is for an electric dipole. Now, let us try to convert the magnetic dipole field formula into the form in which we have the electric dipole field formula. So there is x cube in the denominator there. There is x cube in the denominator here also. In the electric field formula, there is a 2 in the numerator. Okay. So to bring that 2 in the numerator, let us multiply and divide with 2 here. So the magnetic field on the axis becomes 2 mu naught I r square by 4x cube. For now, it's like this. Okay. Can any of you tell me what is K in electrostatics?
One by 4 pi.
1 by 4 pi epsilon naught. Okay, it's something which depends on the medium. Epsilon naught is permittivity of free space, right? So remember, in electrostatics, wherever you get 1 by 4 pi epsilon naught, okay? In magnetism, you get this as mu naught by 4 pi, where mu naught is permeability of free space, okay? So in the electric field formula, there is a K, there's a 1 by 4 pi epsilon naught. In place of that, in magnetism, you will see like we are going to derive some more magnetic field formulas and all. You will notice a similarity between electric field formulas and magnetic field formulas, and you'll see that wherever you get 1 by 4 pi epsilon naught in electrostatics, you get mu naught by 4 pi in magnetism. So we are going to do that here. In order to bring in a 4 pi in the denominator, we'll multiply and divide with pi. So what it becomes is 2. In place of k, you have mu naught by 4 pi. Then you are left with I into pi r square in the numerator. And in the denominator, you are left with x cube. Okay, so this is the same formula for, this is the formula for field on the axis of a magnetic dipole, circular coil. And electric field formula was this. Okay, now we have a 2 here, we have a 2 here. There's an x cube in the denominator, x cube in the denominator. K is 1 by 4 pi epsilon naught. In place of that, you have mu naught by 4 pi. What else is left? In place of P, can one of you tell me what P means?
Dipole moment.
Electric dipole moment. In place of P, here we have I pi r square. So if P is electric dipole moment, then this term here must have been magnetic dipole moment. Okay. Now, of which system is this the magnetic dipole moment? A circular coil. Circular loop, I should say, not coil. Coil is a coil has number of loops, but we just derived for a single loop. So if there is a circular loop like this, or you can visualize normally itself, there's a circular loop like this, carrying a current I, having a radius r, then its magnetic moment becomes I pi r square. I is the current, okay. For this loop, what is pi r square?
Area enclosed.
Area of the loop, right? This area. Therefore, you can tell that the magnetic moment of any loop is current flowing in that loop multiplied with its area. Okay, this gives you the magnitude of the magnetic moment. Now, it's not necessary that there will only be one loop always. There can be multiple loops. Then the magnetic moment, capital M stands for magnetic moment, of a coil. Coil has a number of loops. Okay, becomes number of loops multiplied with IA. IA is the magnetic moment of one loop. If there are n number of loops, then it becomes n times of IA. Their magnetic moments will get added. This is also the magnitude only. We still didn't discuss the direction. Let us go back to the discussion that we had in the previous class. Yeah, in this case, the loop is perpendicular to the screen. Some part of the loop is out of your screen. The dotted part is behind the screen. Now current is flowing upwards in the part which is outside your screen. Now I want you all to curl your right hand fingers along the flow of current. Okay. So, okay, as seen from your side, out of the screen, the current is going up. So you will curl your right hand fingers like this and the thumb will point this way. Okay, like my thumb, is it appearing to the left to you or to the right?
Left, sir.
Left. Okay. But correct only, no? Magnetic field is to the left. Fine. So yeah, you just have to curl your right hand fingers along the flow of current. Then the thumb will show you the direction of magnetic moment. In electrostatics, you tell me, what is the direction of electric dipole moment? Anyone? Dipole has a negative charge and a positive charge. What is the direction of dipole moment?
Positive to the negative.
It's from negative to positive. Okay, electric dipole moment is from minus q to plus q. Okay. Now see here, one side of this loop behaves as the south pole. Okay. Like in this case, the right side behaves as the south pole and the left side behaves as the north pole. Fine. The field is directed, field of this loop is directed from south to north. Fine. So, okay, I'll just indicate the field here. Magnetic field is directed this way. So that becomes the direction of dipole moment for a magnetic dipole. Inside the magnet, whatever is the direction of the field, that is the direction of its magnetic moment. So effectively it becomes from south pole to the north pole. So it's like south pole is negative magnetic charge. Actually, there's nothing like magnetic charge, but we are just drawing an analogy between electric charges and magnetic poles. Fine. So south pole is like negative magnetic charge, north pole is like positive magnetic charge, and dipole moment is from negative to positive, south to north. So here, to get the direction of dipole moment, you just have to curl your right hand fingers along the flow of current, which in this case points to the left. Okay. But how do we generalize this? Like in a formula, if you want to include the direction, how do we do it? Can any of you tell me any vector which indicates a direction perpendicular to a loop? Because dipole moment here is perpendicular to the loop. From right side to left side, it is perpendicular to the loop. So if there is any other vector which is in that direction, we can say dipole moment will be in that direction.
Area vector, sir.
Correct. Area vector. This we had discussed in electric flux also, if you remember. If there is a surface, any surface, it need not be a loop. Suppose there's a surface like this, then area vector of that surface should be perpendicular to the surface like this. It could be in the downward direction also, but it has to be perpendicular. Same thing applies to loops as well. Fine. Now again, as I just said, you could take area vector this way. You could also take it this way. Which way should you take it? The direction of flow of current will decide. So current direction is important and perpendicular to the loop is also important. So in this case, you curl your right hand fingers along the flow of current, the thumb points to the left. So we'll say area vector is this way. We will not consider the other one. Okay, in case of magnetic moments, it's taken like that. We assign a particular direction to the area vector. For every plane surface, there are two perpendicular directions, upward, downward, or outward, inward. But while expressing magnetic moment, we assign the direction shown by the thumb when you curl your right hand fingers along the flow of current. That direction is assigned to the area vector, not the other direction. So magnetic moment is in the direction of that area vector. Therefore, we can say that magnetic moment as a vector is NIA vector. Fine. So any current carrying coil having n number of turns with a current I in it will have a magnetic moment of this much, NIA. Any doubt in this? Basically, this derivation is done by comparing magnetic dipole to electric dipole. Okay, the field produced by magnetic dipole on its axis, we compared it with the field produced by electric dipole on its axis. We got it like this. So if you have any doubts, you can ask. Otherwise, derive the SI unit and dimensional formula of magnetic moment. Units and dimensions should not take that long. Harika is saying SI unit is ampere meter square. Okay, that is correct. See in the formula, what is capital N?
Number of turns of the
Number
coil.
of turns. It's a number, it won't have any units. I is current, A is area. Therefore, the SI unit will be ampere meter square. Dimensional formula?
AL square.
That's all. Ampere will be kept A itself. You can write it as I also, not an issue. Meter is length. So it becomes A L square. Okay. Manasa, you joined a little late. We are just discussing magnetic moment of a loop or a coil, current carrying coil. Okay. Fine. So we'll come back to this point. Okay. We'll come back to magnetic moment a little later. Basically, what we were doing is we were applying Biot-Savart law and the results we derived using Biot-Savart law. Okay. In that process, we discussed the magnetic field produced by a circular loop on its axis, we see that it is similar to electric field produced by an electric dipole. So we drew that analogy and all. But let us continue with this now. So we know the field produced by one circular coil, one circular loop on its axis, right? Now there is a system called a solenoid. Solenoid is basically, you can say it's like a spring itself. It's a tightly wound spring. Okay. So you can imagine something like this. So these are the windings. They should be very close to each other for you to be able to visualize. I am showing them with significant space between them. Okay. Now imagine a current flowing through this system. One second. Right. Suppose a current flows like this. So effectively what happens here is there are a number of circular loops here. Okay, as I said, it's a spring-like coil and the loops must be very close to each other. So each turn is like a circular loop. Fine. Let's draw its axis. This is the axis of the solenoid. Assume its radius is small r. Let's say its length is L. And in that length itself, let's say there are n number of turns. Okay. Now, one of you do this or all of you do this and tell me, just curl your right hand fingers along the flow of current. The solid part of the wire is out of your screen. The dotted part is behind. Okay. Curl your right hand fingers along the flow of current in those loops. In which direction will your thumb point?
Left.
It will point to the left. Okay. That means this system creates a magnetic field to the left. Like this. You can imagine this as a field line. So what happens? This side behaves as a south pole and that side behaves as a north pole. This is what we call as an electromagnet actually. Okay. As I said, this experiment itself, some of you might have done in your lower classes. So this is what happens. The current flowing in that coil creates a magnetic field. Since there are a number of loops, their magnetic fields add up and you get a significant magnetic field. Okay. Now there is another way to denote a solenoid. Now suppose the current is flowing like this. So effectively what is happening in the lower points at these points, I'll mark these points in green. At these points, the current is coming out. Okay. And on the upper side, I'll mark them in yellow. At those points, the current is going into the screen, right? So they don't always draw a solenoid like this. There is an easier way to represent it. They do something like this. Without showing those turns and all, the points where the current is flowing out of your screen, they mark them with dots in a circle. And the points where current flows into the screen are marked like this. Okay. So this is another way to denote a solenoid. Fine. Now what we have to do is we have to find out the magnetic field that it produces on its axis. So imagine this is the axis. There are a number of turns here. Let's assume this solenoid has a finite length L. Just a moment, small adjustments. Basically, it's a spring. Right. At a random point on its axis, let me mark a point, say somewhere here. We need to derive the magnetic field that it produces. Can any of you tell me an idea how this can be done? I'm just enlarging the diagram. How to find out magnetic field at that random point?
Sir, we can treat this system as a collection of circular loops and find the magnetic
Correct.
field at the center of one loop.
Correct. See, as we had discussed in the last class also, generally when you need to derive the potential or field of a system, the first thing you will try is to consider the system as a collection of some system whose field or potential we already know. Okay. In this case, the solenoid is made or is formed by tightly winding a wire. Okay. In circular loops. We know the formula for field produced by one circular loop. We can use that to derive the field at this point, and we integrate that over the entire solenoid. We can get the complete magnetic field of the solenoid on its axis. And why particularly axis? Because we know field of a circular loop on its axis only. Away from the axis, we don't know the field. So in solenoid also, let us not go away from the axis. Okay, fine. So we have to find out one circular loop. We have to consider one circular loop in this, find out how much field it produces and integrate that. Okay, let's consider a circular loop in this. I'll mark it in yellow. Let's say this one. See, the current in the solenoid is I, means every circular loop has the same current I. So this also will be having a current I, but we'll come to that point. The current we'll have to discuss. Imagine the process, like you'll have to write the field produced by this, then you'll have to integrate it and all. Visualize that, visualize those steps a little bit. Like if you think a little ahead, tell me, what is the field? What is the formula for field on the axis of a circular loop? Without approximation, means without taking x much greater than r. What is the actual formula?
So mu naught I capital R square by 2 into R square plus X square whole power 3 by 2.
Okay. Okay, mu naught is a universal constant, leave it aside. I is the current in the loop, which we know. In terms of current only, we'll derive the magnetic field. R is the radius. Now every loop here will have a radius equal to the radius of the solenoid. Small r is fixed, it's not a variable. For every loop, it's the same radius. X is the distance from the center of the loop to the point where you want the magnetic field. This is going to be a variable. Okay. For the loop that we have taken here, you get this distance. For some other loop, you'll have some other distance. No, the point P where you want the field, that point is fixed. But loops are at different distances from that point, so X becomes a variable. Okay. Imagine trying to write the field produced by this loop here. Can any of you tell me how to write the field produced by one loop? what expression will you write for field produced by this yellow colored loop?
So for this one, it will be the same as the formula, except we'll replace capital R square with small r.
Okay, if it's the same as that formula, mu naught I, okay, capital R should be replaced by small r. This is the field produced by one loop. X is a variable. How will you find out field produced by all the loops?
We integrate it.
Okay, correct. Integration has to be done. But whenever you need to integrate something, like integral is basically addition of infinite number of small terms. Okay, so the term that you are integrating should have a dx or a dt or a d theta, something like that. If you integrate finite values like this, now the value you have given here is a finite value. If you integrate finite values, imagine adding infinite number of finite values, the answer will always become infinity. So if you integrate any non-zero term without a dx or anything, without dx, the answer will become infinite, plus infinite or minus infinite. Okay. So that dx term we have to bring into the equation. How can that be done? Okay, what does dx mean? Anyone?
A small change in x.
Small change in x. Now we have visualized x here. Then a small change in x from one loop to the next loop will be this, the width of the loop. Okay, so you have to take loops which have some width. You can't ignore that width, because if you do that, you can't bring the dx into the equation. Still, if you consider that width also, how will you bring dx into the equation? Any idea? Okay, listen. A solenoid, as I said, it's a tightly wound wire. Now, the width that you consider, suppose you take a small width like this, there will be a small amount of current flowing there, this way. If you take a greater width, say from here to here, then the amount of current flowing in it will also be greater, right? So you look at the diagram in the corresponding to the problem now. We took a loop of width dx or thickness dx. The current flowing in that loop depends on that width dx. That way, the current can be expressed in terms of dx, and we can bring dx into the magnetic field equation and we can integrate it. Okay, but still, how can it be done? This is the idea. The current flowing in the width that you take depends on how much current flows per unit width. Okay, so in case of solenoid, we talk in terms of number of turns per unit length. Number of turns was n, capital N, per unit length. Length was L. So this becomes n by L, right? We denote it by small n in case of solenoid. Okay. Now you know number of turns per unit length. Let us call it small n. What length are we talking about? Length of the solenoid. Now if you see dx is a small part of that length only, no? In that dx, let's say the number of turns is dn. So basically what I'm saying is this yellow thing that I have drawn, it's not just one turn of the wire. There could be a number of turns in that. Okay, but they are very close to each other. You can take it as one turn itself. But the currents have to be added, no? Even if two wires are very close to each other, it doesn't mean, like suppose there are two wires having a current I in one and 4I in one. You bring them very close to each other, you can treat them as a single wire having how much current? 5I. Okay, it's not I or 4I. You have to take net current as 5I. So we are doing the same thing here. In this width, there are a number of turns like this. Fine. What is that number of turns and all? We'll derive the expression. And the current in that width dx will be the sum of all those currents. That idea we'll be using in a solenoid. So number of turns per unit length, capital N by L, let's equate it to small n. Now, what is the length of that length or thickness of that loop that we have considered dx? So this small n should be equal to dn by dx, number of turns in that width divided by the width. So the number of turns in that width becomes small n into dx. Okay. Now each turn has a current I. Therefore, the total current in that width, total current in the element that we have taken, will be number of turns multiplied with current in each turn. Okay, let us go through this once again. We had to find out the net field produced by the solenoid at some point inside it on its axis. There are a lot of turns, circular loops. We can write the field produced by one circular loop, but there are a lot of circular loops there. Okay. For each loop, sorry, we can't write the field expression for each loop and add them up, because for each loop the distance x will be varying and we don't know what exact distance the loops are at. Okay, so integration is the way to proceed. We are writing the expression for field produced by one loop at p and trying to integrate. But when we write expression for field produced by one loop, we don't get a dx or anything to integrate. So we are trying to express this same field in terms of dx. Because x is a variable, we are trying to bring in dx. Now dx is the width of that loop. Now we know how many loops are there in the total length. So in that length dx, how many loops are there, we are deriving. So it becomes small n into dx. Small n is number of loops per unit length. Multiply that with the length dx, you'll get the number of loops in it. Multiply with current, you'll get the total current in that yellow element now. Okay, so now in place of the current here, this one, we will have to write this. That is the current in the yellow element. For one loop, it is this itself. Okay, but in that yellow element, there's not only one loop, there could be a number of loops, we don't know. So we'll have to go this way. Therefore, magnetic field produced by the element becomes mu naught I into pi r square. In place of I, we'll now write ni dx into pi r square divided by r square plus x square whole power 3 by 2. Okay, there's a 2 also in the denominator. Fine. That is the field produced by one element. Any doubts in this? Fine. We now need to integrate this. Let me copy the diagram also. To get the net field at the point P, we'll have to integrate this field expression. Mu naught small n I pi r square 2, they're all constants. Let's put the constants aside. You can write this as k. What will you be left with? Dx by r square plus x square power 3 by 2. How can this be integrated? Any idea, anyone? Okay, see, generally, fine, you'll learn it in mathematics integration in a little detail also. Whenever you see r square plus x square or a square plus x square or 1 plus x square in the denominator, you should get the idea that you have to use trigonometry. Okay, yeah, integration by substitution, correct. So what we are going to do here, I'll enlarge this diagram a little bit. We will visualize an angle here. Now the distance x is visible. This distance becomes r, the radius. XR. Now connect the edge of that loop to the point P. Okay, call this angle as theta. Right? So you can write tan theta is equal to, tell me quickly, one of you, in that right angle triangle, what is tan theta equal to?
R by X.
R by X. So you can say X is equal to R cot theta. Differentiate this. Okay. You get dx is equal to R, derivative of cot theta, minus cosecant square theta d theta. So in place of dx, we are going to write this. And r square plus x square. There is r square plus x square in the denominator. We have to replace x now. Okay, we are changing the variable. We are writing x in terms of theta. X is equal to r cot theta. We'll write that here also. The constant will substitute later. So this was the small magnetic field produced by one element. This now changes to K. In place of dx, we are going to write minus r cosecant square theta d theta divided by r square plus x square. X square becomes r square cot square theta. So denominator becomes r square into 1 plus cot square theta whole power 3 by 2. Is there any trigonometric identity for 1 plus cot square theta?
Cosec square theta.
Cosecant square theta. Okay, fine. So this part becomes cosecant square theta. Now the denominator has whole power 3 by 2. So effectively this whole thing becomes minus kr cosecant square theta d theta divided by r square whole power 3 by 2 becomes r cube. Cosecant square theta whole power 3 by 2 becomes cosecant cube theta. One cosecant will be left in the denominator and r square will be left in the denominator. Therefore, the small magnetic field produced by one element here becomes minus k by r square. There's a cosecant in the denominator, goes to the numerator and becomes sine theta d theta. You integrate this with proper limits, you will get the magnetic field due to the entire solenoid. Again, let us visualize in the diagram. We need the limits for theta now. We have to ensure that all the circular loops get covered. Okay. So let us write thetas for the initial circular loop and the final circular loop. This diagram I'll use only for the limits. Okay. For the first loop is here at the left end. If you connect that to this point, call this angle as theta. That means this angle is also theta. So this is the starting value of theta, initial angle. Okay. And see, theta is taken with the left side. Fine. If you go to the last point, the other end of the solenoid, theta must be this angle. This complete angle is theta. Let's call this part as alpha. Now we know alpha is 180 minus theta. And if that angle is alpha, this angle is also alpha. So the final limit, let's call this as theta 2. That internal angle, will take it as theta 2. So the final theta should be pi minus theta 2. Now, why am I writing it in terms of theta 2? Why don't I just take it as that final angle? Because usually when you are given a problem, you can visualize these angles. This inside angle and this inside angle can be seen by you. But those angles directly are not the limits. Okay, this side it's fine. this side, whatever is the inside angle, let's say this is some 30 degrees, that itself is the initial limit. Okay, I mean lower limit. But that side, let's say this angle is 60 degrees. 60 degrees is not the upper limit of integration. 180 minus 60 is the upper limit of integration. Okay. Fine. So these are the limits for us now. Theta 1 to pi minus theta 2. So we'll now do the integration. Therefore, total magnetic field on the axis of the solenoid becomes minus k by r square. Okay, let us substitute that constant also now. What was k? Mu naught n I by 2. That was k. So minus mu naught ni by 2 and r square is there. You'll have to integrate sine theta d theta from theta 1 to pi minus theta 2. So minus mu naught ni by 2 r square. Integral sine theta we know is minus cos theta. Minus s cancel. We still did not substitute the limits. Wait, integral sine theta is cos theta or minus cos theta?
Minus cos.
Minus cos. Okay, fine. Now substitute the limits. Upper limit pi minus theta 2. Cos of pi minus theta 2 becomes minus cos theta 2. Minus of lower limit is theta 1. Cos theta 1 is cos theta 1 itself. We'll write as it is. Put the minus outside. Okay, we'll see where we got the minus from. Mu naught ni by 2 r square. Cos theta 1 plus cos theta 2. Let us just check. Why did we get this minus? I think it is with dx itself. Usually that is where the problem comes. Listen. If x increases, we took x to the left side. From the point P to the left, we took x. Dx is also going that way. If x increases, what happens to the angle theta? Does it decrease or increase?
Decrease, sir.
Okay, just a moment. We took x that way. Dx is like this. So if x increases, theta has to decrease. But that justifies the minus sign, right? If dx is positive, d theta should be negative. So we have a minus sign here. Is x taken from P to there or there to P? That is what we have to be clear about. Just a moment. Or does the minus just indicate that the field is to the left? That is also okay only. That makes sense. No, field is to the left, so we got a minus sign. Let it be, not an issue. Okay. We'll see if there's any way to remove that minus. For now, the only explanation I see is that field is to the left, so we got a minus sign. That is reasonable. So the magnitude of the magnetic field on the axis of a solenoid, finite solenoid, becomes mu naught ni by, once again, dimensionally this does not seem to be correct. we got K as mu naught Ni by 2. Okay, there's a pi r square here also, no? Included in K. Yeah. So in the numerator, we have to write just a second. In place of I, we wrote n dx multiplied with I. Where did pi come from in the numerator? Like here in the formula for magnetic field on the axis, there's no pi in the numerator. I wrote it by mistake. So only r square. Yeah. Now that r square should be included here. Gets cancelled. Now it is dimensionally fine. So mu naught Ni by 2 cos theta 1 plus cos theta 2. Okay. Did any of you ever do this derivation? Like for some of you, this chapter is complete. No, did you do the derivation?
Yes, sir.
Okay, good. And what about the minus sign? You didn't get the minus there?
No, sir, we got the minus sign. They just
Minus
told us
will be there. I think it is to indicate the direct. What did they tell you?
they told us to take the magnitude. That's it.
Okay, fine. Right. So this is for magnetic field on the axis of a finite solenoid. And see, finite solenoid is for JEE advanced. In mains, they don't ask about finite solenoid. Now, let us discuss some cases of this. Okay. Let's take this diagram. So here, if you visualize theta 1 and theta 2, okay, you are trying to find out the magnetic field at a random point on the axis. You connect that point to the left end. This angle is theta 1, and connect the point to the right end of the solenoid. This angle is theta 2. Okay. If the solenoid is infinitely long, what will theta 1 and theta 2 tend to become? Zeros. So for infinite solenoid, field on the axis becomes, see, if theta 1, theta 2 are zeros, cos theta 1 will be 1, cos theta 2 also will be 1 plus 1, 2, 2 gets cancelled. You get mu naught Ni. There is another way also to derive this result using Ampere's law, which we'll discuss next class. But for now, we have done it using Biot-Savart law. Okay. Or the results we derived using Biot-Savart law. Okay. Next, semi-infinite. Solenoid at one end. Semi-infinite solenoid means one end is visible, the other end is at infinity. And I am particularly talking about field at one end of the solenoid. So that point P, the point where you are calculating the magnetic field, should be taken at the end. Okay, just a moment. Imagine this as a solenoid. Okay, one side it extends to infinity. Let's say on that side it extends to infinity. You need magnetic field at this point. Then you connect that point to the ends of the solenoid. You see one angle becoming 90 degrees. The other angle at the other end will be tending to 0. Okay. So if one angle is 90 degrees, you'll get one 0 and one 1. Okay. So the bracket will become 1 and the field will be mu naught Ni by 2. Okay. Anywhere comfortably inside a solenoid, it is a long solenoid, it is mu naught Ni. But if you go to the end of a long solenoid, the other end is very far away, but this end, you are at this end. then the field will be mu naught Ni by 2. Okay. Now see, in reality, there are no infinitely long objects. Fine, finite only. Now you consider this case. Assume, okay, let's consider this diagram. Assume the solenoid is very thin compared to its length. Let's say it's like this. What are theta 1 and theta 2 tending to become? We took a random point P somewhere. Okay, I hope you all were able to see that point. Let me just show you the diagram on this side. Point is there only, you can see the angles, no, theta 1 and theta 2. Okay, I'll remove alpha and write theta 2. As the solenoid is made thin, what do those angles theta 1 and theta 2 tend to become?
0, sir.
They tend to become zeros. Okay, as we make this solenoid thinner and thinner, those angles will decrease. If it's very thin, both the angles tend to become 0. Okay, if the angles tend to become 0, what does the field become? Or how much does the field become? Again, cos theta 1, cos theta will become 1 and 1. Mu naught Ni by 2 into 2, it becomes mu naught Ni. So field on the axis inside a thin finite solenoid is mu naught Ni itself. Don't go to the extreme ends. Fine. At the end, it will be mu naught Ni by 2, but anywhere comfortably inside the solenoid, it is mu naught Ni. So we take it to be a uniform magnetic field. In our syllabus, we assume the magnetic field inside a long solenoid or a thin solenoid is uniform. You can see this. It doesn't depend on the angle theta angles anymore. Okay, it doesn't depend on where you take the point, because anywhere comfortably inside, you connect the point to the ends of the solenoid, the angles will be tending to become 0. Okay, so we can assume the field is uniform inside the solenoid, except at the ends, we ignore that edge effect. Okay, we say in a thin solenoid, the field is uniform mu naught Ni. Is this clear to all of you? Can any of you tell me how to get a uniform electric field? Which system of charges produces a uniform electric field?
Sheet charges.
What did you say?
Sheets.
Sheet. Okay, an infinitely large sheet of charge. Correct. We discussed one more case also, if any of you remembers. Can you tell? Another system which produces a uniform electric field. Okay, I'll quickly revise that. If you take a solid sphere, uniformly charged solid sphere, and you make a spherical cavity inside it. Okay, the system should be a sphere, the cavity should also be spherical. Okay, we solve this as a problem. Then the field inside this space will be uniform. Okay, positive charges, no, directed outwards. Field in that space will be uniform. Go through that result once, it's an important derivation. Anyway, in magnetism, a solenoid is a system which produces a uniform magnetic field inside it. And as of now, we have restricted our discussion to the axis of the solenoid. Using Ampere's law, we'll be able to prove that the field is completely uniform, not just on the axis, everywhere inside it will be uniform. Okay, fine. So we derived magnetic field of a finite solenoid at a point on its axis. We extended that to an infinite solenoid, and then thin solenoid also. Okay. Now let us discuss magnetic moment in detail. So as I said, we derived the result for a circular loop. We showed a circular loop behaves as a magnetic moment. We derived the formula for its magnetic moment also. Okay, I into pi r square, we wrote it as I into a. That is true in general for any loop, not just circular loops. Okay, so magnetic moment of any loop can be expressed as Ni a vector. Let's take one question based on this. See, if you know the area of a loop and the current flowing in it, and if you know the number of turns, okay, in that coil, number of loops in that coil, you can easily tell the magnetic moment. That's fine. The tricky part is, what if the loop is not planar? Okay, if it's a flat loop, you can tell its area. Triangle, you can tell square, you can tell circle, you can take, they are all two-dimensional. Okay, but what if the wire is bent? You may have solved questions like this also, but let's just discuss. Suppose there is a wire bent in this shape. So it was a square, but now it is made into like it is folded like this. So you can imagine this as the z-axis, this edge along the x-axis, this edge along the y-axis. So this is a loop only, right? Let's say the current flowing is I. I'll give you the dimensions also. Assume this is a by 2, this is a by 2, and this side is a. Same for the others also, opposite sides also. Had it been a flat square of side A carrying a current I, you could have said its magnetic moment is I into area of the square is A square. How will you express the magnetic moment of this kind of a system? Magnetic field is a vector quantity. We need to assign a direction also. Had it been a flat surface, like the palm of our hand, we can say the area vector is like this. But this is not a flat surface, it's a bent surface. How can we even assign a direction to its area? Yeah, Yash, what do you want to say?
Sir, we can treat it as like two surfaces, like two loops.
Correct. Okay, we can treat it as a combination of two loops. See, basically the idea here is, the hidden idea here is that magnetic moment is a vector quantity. Okay. If you are given a system and asked its magnetic moment, if it's flat, okay. If it's not flat, what you can do is you can treat it as a combination of flat systems. And since magnetic moments are vector quantities, you find out the magnetic moment of each flat system separately and add them. Okay. But see, we only know that a current carrying loop behaves as a magnetic moment. It has to be a complete closed loop. Only then we can write the magnetic moment. Yes, you only tell me, elaborate your idea, how to make this or take this as a collection of two closed loops.
Sir, we have here 2 points, right, which are like at which the loop is bent.
Can you repeat which points are you referring to?
Like where the square frame is bent.
The right angle. Yeah, yeah. All these points as A and B. What can be done?
Sir, where there we can join two wires,
Right. Correct.
thin
Correct.
wires placed
Got it.
near
Got it.
them.
Yes. So actually the original diagram that I had drawn before erasing that part, you can consider this system as one loop like this. In which plane is this loop? YZ plane. And another loop like this. and this second loop is in the XZ plane. Now, what about the currents? Actually, in the question given to you, there was no current in this part. No current flowing along the Z-axis. But what you can treat it as is two currents flowing in opposite direction. You can take a current I going this way and another current I in the other loop going this way. So effectively what happens, this becomes one loop, one flat loop, and this becomes another flat loop. Okay. Now for the orange one, you all do this. You know how the current is flowing, okay? Curl your right hand fingers or imagine curling your right hand fingers along the flow of current in the orange loop. Which way does the thumb point? Isha, can you tell the direction of the thumb?
So to the left.
To the left, correct. Good. And to the left means in the negative x direction. Okay. For this coordinate system, left is the negative x direction. So the magnetic moment of that orange part is this way. Let's call that as M1. Good. Harika, you tell me, if you curl your fingers along the flow of current in that green loop, current is flowing like this. Which way does your thumb point? Curl your right hand fingers.
The same directions.
No. How can leftward direction be perpendicular to the loop at all? To that loop, this is
Sorry,
not
sir,
a...
I mean towards right.
No, it won't be towards right also. How is the right direction a perpendicular direction? Right direction means x-axis. The loop is in the XZ plane. X-axis will become parallel to the loop. Harika, you think of the loop. I mean, you imagine the loop being placed on your table.
Sir, it will be towards Z direction.
See, visualize this first. X is to your right. Z is
Yes.
towards you. And Y is upwards. Okay. The loop is in the XZ plane, means it's in the horizontal plane, the plane of your table. Curl your right hand fingers along a loop in the plane of your table. Which way does the thumb point? You have to curl your right hand fingers this way. On your table, you have to curl them like that. Okay, as seen from this angle, Harika, in which sense is the current flowing in that green loop? Clockwise or anti-clockwise?
The clockwise, sir.
Clockwise. Imagine a clockwise arrow on your table. Just curl your right hand fingers along that.
It is going out of the planes.
Means upwards.
And
Out of your table means upwards only, no? Uh, okay, others, any answer? Which way is the thumb pointing?
Minus Y.
Minus Y, it will be pointing downwards. If you curl your right hand fingers this way, the thumb will point down like this. Harika, are you getting that or not? No?
no, sir.
Okay, wait, I'll show you with a sheet of paper maybe. Directions are important, otherwise your answers will go wrong. Okay, this curved arrow, does it appear clockwise to you all or anti-clockwise?
Clockwise.
Clockwise. Okay. This is my right hand. I'm curling my right hand fingers along that clockwise arrow. Then thumb is pointing into the paper, into the sheet of paper. Now the same thing is in the horizontal plane. It's like this. Okay, you can imagine the edges of this paper itself as that loop. So curl your right hand fingers clockwise, the thumb will be pointing downwards.
Sir, are we looking at this loop from above or from below?
Just a moment. Like if it's like this, it's from above only. I mean, it's like you are in the first octant, X positive, Y positive, Z also positive.
Sir, if you squint your eyes a little, it looks like you're looking at it from below.
Yeah, I'm trying to look at it that way. Just a moment. Okay, you want me to imagine it as looking from below. So look at it from.
Sir,
Wait, just a moment. If you are looking at it from below,
In that case, it will be positive y-axis.
no. If you are like, if this is like looking at it from below, do you think this branch that is there, this one, is it like towards you or away from you when you're looking at it from below?
Towards me.
From the origin, I'm talking, reference is from the origin. Okay, from the origin, this line is up. If you're looking at it from below, is it towards you or away from you?
Somewhat towards me.
Looking at it from below, can it be towards you? Just a moment. Okay, let me fold this sheet of paper. So half square, half square. Okay. The way I have given the question, I'm looking at it from this. Okay, you don't see the paper. Just a moment. So the way I have given the question, it's like this. I am looking at it from above. So for me, okay, let me show from your perspective only. Okay, you.
So if you take your hand towards your top right, that's the view, the other view that can be considered.
No, wait. The view I have given you in the problem, I'll show you first. It's like this. Okay, the origin being here. Origin is here. This is the positive x-axis. This upward is the positive y-axis. And this bend that is there is the positive z, which is towards you. Okay, now you want to look at it from below. If you want to look at it this way, okay, I have rotated it. Just a moment. You want to see it like this. Yeah, like this. If you see it like this, I mean, where did I mark the origin? I marked the origin here, no?
Yes.
Then this is like going away from you. If origin is here, this edge is going away from you, no? It becomes the negative z direction. It can't be positive z. Okay. If origin is marked here, then this edge is going away from you. And away from you, like there is a rule for the Cartesian coordinate system. X cross y should always be positive z. Okay, like in this case, x is to the right, y is upwards. X cross y, curl your right hand fingers this way, the thumb will point outwards. Okay, for me this is outwards. So out of the screen is positive z for you. It's a rule. You can't call the other direction as positive z. In the Cartesian coordinate system, it's a rule. And according to that, this perspective is from, I mean, it's like top view at an angle, not exactly top view, angle from above only. Okay. Anyway, that second magnetic field, not magnetic field, magnetic moment will be directed downwards like this in the negative y direction. This is the second magnetic moment. Now we want the effective magnetic moment of this entire loop. Okay. So as I said, magnetic moments are vector quantity. So you'll have to do m1 vector plus m2 vector. Let us write their magnitudes now. m1 as a vector, we know magnetic moment formula is NIA. N is number of turns. There's only one turn here. I is the current. Now each part here is a rectangle. One side of the rectangle is a by 2, the other side is a. So area becomes a square by 2. That is m1's magnitude. Direction is minus I cap. Similarly, m2. It'll also have the same magnitude. Direction is minus j cap. Add them as vectors, you will get the effective magnetic field. Sorry, effective magnetic moment. So in case the loop is not flat, this is how you are supposed to do. Okay. So there are some more things left in this chapter, like Ampere's law, and then behavior of a magnetic dipole in an external magnetic field. That will be analogous to behavior of electric dipole in an external field. We'll discuss about torque acting on the dipole, okay, and such things. Then we will move on to the working of a galvanometer. But in the next class, we are going to solve some more problems based on magnetic moments and Biot-Savart law applications itself. Okay, next class will be on Tuesday. We'll solve some problems based on these. Okay, after that, we will move on to Ampere's law galvanometer. Okay, if you all have any questions, you can ask.